principal applied research scientist at NVIDIA, focusing on deep learning for medical imaging. Over the past several years, he has worked closely with clinicians and academics to develop deep learning-based medical imaging computing and computer-aided detection models for radiology. He was awarded the MBZUAI Young Scientist Publication Impact Award, and his research interests include active learning, automated machine learning, collaborative model deployment, and federated learning.
Thank you for the introduction, and thanks again for the invitation to speak here. It's been really interesting so far. Okay, so I'm going to talk a little bit about the kind of the works and tools that we're working on at NVIDIA. One of the main or important things in healthcare is, of course, to build robust and generalizable models. We think there are basically these kind of three challenges, starting with the data preparation, annotation of data, which is like a whole topic I'm not going to address today, but if you're interested, talk to me. And then data diversity to cover all kinds of variations of human populations, diseases, and privacy, right? Patient privacy is of utmost importance, and governance of the data is an important issue. So these last two topics, we kind of believe that federated learning is at least a partial solution to address these issues. And so we've been focusing on applying that. Again, I think Marco also mentioned this. It's a little bit in contrast to the cross-device scenario that we see in the mobile phone sector. We've been focusing on this kind of cross-silo scenario where we have maybe tens or hundreds of larger hospitals with their local data sets and a data center with reasonable compute, stable internet connections. But I'm not saying that like this first scenario is not useful for healthcare. Like in healthcare, you can see wearable devices, blood pressure tracking of patients that could be really useful or really interesting in the future. If you're interested, we've written this positioning paper some years ago that goes into the benefits for different stakeholders in healthcare, starting from the clinicians to the manufacturer, scanner manufacturers. Of course, we believe it's a promising technology that can be applied in this field. So we've done a couple of real-world use cases so far, starting from brain tumor segmentation, where we started off with a simulated scenario. There was a public data set called the Brain Tumor Segmentation Challenge data set that originates from several hospitals, I think mainly in the US. So you kind of know the original acquisition side of the data. You can separate, partition the data based on origin and do some nice studies with real world data sets in medical imaging. But then we moved pretty quickly to applying this in the real world where data was located on hospital sites together with Jereshri, who's also here. We worked on mammography classification involving 7 hospitals in North America and South America. Around the same time, we also had a work on prostate MRI segmentation. So that is looking at a 3-dimensional data, medical image segmentation network involving 3 US hospitals. We had some kind of proof of concept going on in Asia between Japan and Taiwan to look at pancreas segmentation. And then most recently, we had a study that was published in Nature Medicine involving 20 hospitals around the globe, looking at COVID image analysis. So I always like showing this example from the Taiwan and Japan data, where the interesting thing is that one client has only healthy cases. So you have images with background and pancreas annotated, while the other client only has cases that have actually tumors in the pancreas. So you have 3 classes, basically background, pancreas, and tumor. So you can see if that client 2, which has the tumor cases, that model trained has a kind of a bias towards predicting that there's a tumor in the pancreas. So it generates this kind of false positive here, which of course is something you don't want to have. Don't want to let a patient go through all the follow-up treatment to figure out if it's really a tumor. While the global model learned with federated learning does correctly segment this pancreas as a healthy pancreas. And similar, vice versa, the client, the model only trained on healthy pancreas. Of course, it has no concept of a tumor, so it's completely missing that area. While the global model is doing a reasonable job at least detecting the tumor region there. So, as I mentioned, the largest study we did was this Nature Medicine paper. You can see, of course, this was a pretty large collaborative effort in order to get off the ground. We looked at predicting the oxygen requirements of a patient arriving at an emergency department with symptoms of COVID-19. So this was actually a multimodal model that looked at a chest X-ray and different EHR values like patient demographics, blood works to predict the oxygen treatment, going from no treatment room air to ventilator, and even predicting death in 24 hours and 72 hours. So we trained actually 2 models there. And then here again, this is what Marco mentioned, right? This is a real world data set where you can see the heterogeneity in non-idealness of the data, both in terms of quantity of data, the top right, intensity profiles of the X-ray images is very different depending on the scanner manufacturer, patient population, all affects that. And then also different features from the EHR, like here I'm just showing the patient age, which can, it's mostly the risk population around 60 years old, but we also have like some pediatric hospital where you can see there are some very young patients who were affected by COVID. So it's a real diverse data set that we now can access through federated learning. And then here you can see we trained a local model. So each client trained on their own data. This is sorted by the data set size. So client 1 is the largest data set, and client 20 is like the smallest amount of data. I think they're only around 20 cases. So you can see they cannot train like even a good model that generalizes to their own validation data. But the global model is kind of performing well across the board. And you can really see in the generalizability. So here we're plotting the performance of each locally trained model based on, with respect to data set size, evaluated on all the other clients. So excluding the performance on their own validation data. Again, you can see that even the largest clients, they get like a boost in generalizability when comparing to the global model. So then we also did an external validation on sites that were not included in the federated learning study and showed that this global model can generalize quite well to these unseen sites with ASE of 0.94 and 91 for the 72 hours, which the more difficult task, so it's kind of expected. Okay, so next I'll talk a little bit about some of the challenges of FL, which we are trying to address. So these are more research works. Again, to illustrate this, another example of the heterogeneity of the data. When you really collect these like data sets in the wild, right? So you have mammography, data intensity histograms that look very different across the clients. But again, quantity and the labeling standard can be very different depending on how different hospitals annotate their data. So in order to address this, we basically investigated 2 lines of work so far, mainly focusing on the personalization, how that can address that, and I would say combination of these can be complementary. We're looking at hyperparameter tuning, because that's probably one very important thing to get right in this federated learning setup to address these issues. So yeah, so the simplest approach, of course, for the personalization is maybe to just do local fine-tuning after you have your global model. And we show that here in this mammography data set for most clients, they can achieve better performance on their local test data after fine-tuning. And they still get a benefit of the federated learning by starting from this good global model as a kind of a good starting point. But that has the risk that you're probably losing some of the generalizability. Again, so this trade-off is important. We also looked at doing some sort of automated neural architecture search. So each client can actually find the best model architecture for their data set, which can also boost the performance locally. And most recently, we have this work, which is looking at a federated supermodel. Basically, the assumption here is that we have a model selector that we can predict to say on a case-by-case basis which model from which client is the most suitable to predict this image. So it acts a little bit as an ensemble, and in that way it can address heterogeneity and also apply some personalization. If you look at some comparison even to the centralized data set here, which is kind of an upper bound, you can see that because the ensemble is a stronger model, right? So we can even perform better than the centralized data set. Okay, and on this hyperparameter tuning or auto-federated learning, as we call it, we've done a couple of works. We started with maybe the most obvious hyperparameter in the federated learning setting is these weights you use for averaging. Typically, they're based on heuristics, right? A data set size or something like that. So we thought maybe we can find a data-driven approach to learn these averaging weights automatically. So in this approach, the server sends all the local models to each client, and they then use gradient descent or some gradient-based optimization to learn the best combination of the models. And we model the weights as a Dirichlet distribution, so you can then sample from the distribution to get the next set of weights for the next round. So you can see that these weights are adapting as the training goes on. And basically from the same initialization, we can see that these weights that are learned from the data actually correlate quite well to the heuristics that people have been using, like the data set size. And then here, some example that actually performs better when segmenting, again, on a real data set, here, COVID lesions in a lung CT scan. Now at ECCV this year, we also kind of extended this idea to more hyperparameters, right? We have actually a large set of hyperparameters that you now can tune. Starting from on the server side, if you do some adaptive optimization on the server, we can have a server-side learning rate. We have learning rates on the clients. We have number of iterations. This could be extended to including different loss functions and all of these kind of things by using an online reinforcement learning agent to predict the next set of hyperparameters for the next round. Again, here with Cipher 10, we simulate 8 clients, heterogeneous settings, so different amounts of data, different labels. You can see that the weights kind of converge to some stable setting in the end of training. So that way we achieve a better performance. And then you can do these kind of analysis to look at the importance of different hyperparameters for your setup. It's kind of neat. We also apply this to some real-world data sets, but I'm going to skip that. Sorry, how much time do I have? So, okay.
5 to 10 minutes.
Okay, so I went a bit fast, I guess. So yeah, the next line of work we looked at is actually the security and privacy aspects of federated learning, just to kind of understand where the state of the art of the attacks is for the healthcare application. The main concern is about the data leakage, I would say, right? Because that's what we want to try to preserve. So we looked at a malicious server that intercepts the client updates and tries to reconstruct the data, similar to what Salman showed earlier. Here we looked at trying to get some more high resolution images. So these are like your standard ImageNet resolution 224 by 224. We tried, I guess this is probably difficult to see, but we tried to insert some artificial text here to see if maybe that can be recovered. Sometimes in the X-ray, you actually have the imprinted text with name or date of birth, which is of course a privacy risk. Then we noticed that if you actually use like an off-the-shelf ImageNet pre-trained model that involves batch normalization, and the clients update the batch norm layers locally, then these standard attacks that have been recently published actually don't really work that well. So like we couldn't get anything to work. But by actually somehow utilizing the batch normalization updates, we can define an additional batch norm loss to then get a very good-looking reconstruction, right, with a high fidelity. It doesn't manage to capture the text, but I think the patient shape is pretty well preserved. Of course, one should notice that this is based on the gradient updates based on one image and one iteration step, right? So it's like, we call this like a high-risk client that is doing something that you should really avoid, right? Sending update just based on one image. But then we can now use this to quantify the data leakage based on batch size of your update. It becomes harder. Or if you do iterations over different images, of course, it's harder to reconstruct. Similarly, if you apply calibrated noise, so like a different privacy approach, we can see that the reconstructions becomes much harder. And then so in order to be able to compare across different clients, right, each client has their own data set. Some of these, here we use SIM as the similarity metric between the original image and the reconstructed image. Of course, that will depend on the reference image that you use. So these SIM values might not be directly comparable between the different clients. So here we introduce a relative data leakage value that compares the similarity between the reconstruction and the original image and the similarity between the reconstruction and the image prior that was used initialize the attack. So in that way, we get values that are more comparable across the different clients. And you can see that client 9 is the one just sending updates based on one image, one iteration. So it's like the high risk. And it has a relative data leakage above 0, which of course indicates there's actually data leakage happening. While all the other clients, they have like larger batch sizes, I think we went from 4 to 8, and number of images from 16 to 512 or something like that before they send an update to the server. So they don't really have a risk of leaking information there. And then of course you can also plot the accuracy and how differential privacy affects that. So I think this is pretty well understood now, right? Larger training sets help improve the security, doing longer local training and larger batch sizes, while vice versa is of course more insecure. I just want to mention that this is also all dependent on the model architecture that you're using. So we have also done some work in using transformers where some of these attacks actually seem to work better than for CNNs. So this is something that I think the field needs to further investigate and be aware of. But I think due to the token embedding, you can actually get more realistic, more high fidelity reconstructions from the updates from a transformer network. We also investigated some split learning approaches. So here, the assumption is that different hospitals have data for the same patient. It could be different image modalities here for MRI images. But they want to train a segmentation model for tumors using all this available data, right, for each patient. So we're implementing a split learning version of a unit called split unit. So here, only one side has one modality and the labels, while the other sides only have the images. But they're kind of sending activations and gradients back and forth. And again, looking at the attack, so here we want to study kind of the upper bound of the security risk. So this assumes the attacker has access to the state of the model, sending the activations. So it's like a white box attack. If you know that state, you can actually, in the first layers of the unit, if you invert these activations, they're basically one indistinguishable of the original images. As you go deeper, it's more difficult to reconstruct. So in order to see how different approaches can be used to protect against this type of attack, we also applied a dropout of certain activations, which seems to be quite effective, and also adding Gaussian noise seems to be effective. I don't see that, sorry, I'm not showing the effect on the model accuracy here, but we achieved like a little, pretty sensible trade-off between the protection and the model accuracy. But as a summary, I think the whole security aspect in federated learning is multi-layered, right? There's this identity security, secure communication, but then you have to consider all these additional tools like differential privacy, homomorphic encryption, secure multi-party computation. And something I think which will be more interesting is the confidential compute, like a hardware-based solution that can make your training more secure. Okay, so finally I want to mention some of the kind of software tools and community efforts that we're also involved in. One thing is our SDK that was used for all these kind of real-world studies that I talked about has been recently made open source. So it's like a lightweight Python program that you can use to run this collaborative learning and over the internet. We approached the whole problem by designing a very general purpose distributed compute framework. It's basically with these two main components on the server, we have a controller that is basically implementing your workflow. Let's say in the federated averaging scenario, you just do like a scattering and gathering operation. So the server sends a model to each client. Clients are executing this task, which we see on the left box, which might be local training to send back the results, and then the server controller can do the averaging. On both ends, we have these filters that can be optionally be applied, like to do differential privacy, compression, or encryption. In that way, you're really open to implement many different algorithms. We have a set here that's already available, kind of as examples. And we also have a simulator that can use like your code that is both working in the simulation and real world. It's like the same kind of code can be used both for the simulator or real world. You can look at different synthetic splits of data heterogeneity, different algorithms. It's the same. And then just to mention, we do have some components for differential privacy or homomorphic encryption, where in our setup, it's a little bit different to the secure aggregation. It's actually doing the whole aggregation in encrypted space on the server. The server never has a decryption key, so it only sees encrypted values, sends back the aggregated model that is encrypted to the clients. They then decrypt to continue the local training. Here's a little shout out to one of the companies that we're working with. They're building basically the Rhino Health. They're building all the infrastructure that you need around the federated learning algorithmic piece, right? In healthcare, we have things like the connection to the PACS system, which stores all the images, the patient records. Then how do you annotate that? How do you define your cohorts on different sites? So experiment management, traceability, it's all built around this component, which is NVFlare, which is basically doing the training. So you can see there's a lot of work actually to provide this like end-to-end platform that you need to do this efficiently. And we're also working a lot on some open source community efforts for medical imaging. It's called MBZUAI, so it's like an AI accelerated framework for medical imaging. We are starting with customized application for radiology, so like 3D networks, transformations, custom loss functions, they're all provided here. Again, Charashvi and I are involved in leading, together with Daniel Rubin from Stanford, we're leading the working group for federated learning within MBZUAI. So here, a lot of the focus is around maybe providing examples of how do you use these different frameworks that are currently available. Like Marco mentioned, there's like a whole list of dedicated frameworks for medical imaging. Even how can we maybe standardize some of these, come up with reusable components. And most recently, we implemented a little client algorithm standard. So it's a standardized API that can work with the MBZUAI components. So in MBZUAI, there's something called a bundle, which defines your whole training workflow, both for training and evaluation, which is these bundles are being made available in the model zoo. So we have like a selection of different bundles for different applications. And the idea is that this customized, standardized client algorithm API can be implemented by different FL frameworks to then execute MBZUAI bundles off the shelf, basically. Oh yeah, and with that, thank you for your attention.